Question 4. Lactic acid and the pyruvic acid both contains two functional groups. For the lactic acid, we know that it has a carboxyl group and hydroxyl group. So these two functional groups. And for the pyruvic acid, it has the carbonyl group and the carboxyl group. So these two. Okay, these are the functional groups in there. And part A1, explain why lactic acid exists as optical isomer. So the lactic acid, we need to find the chiral carbon. So among these carbon, just 3 carbons here. So this carbon cannot be the chiral carbon because with 3 hydrogen. This carbon is just 3 atom bonded to that. So this is not the chiral carbon. So this carbon with 1 group, 2 group, 3 group, and 4 groups, 4 different groups bonded to this carbon, and we know that this is a chiral carbon. So when a compound with chiral carbon, therefore it can form the mirror image that is not non-superimposible. So this is the optical isomers means. Okay, so it has a chiral carbon which enable it to form non-superimposible mirror images. Okay, which is the optical isomers again. Give the systematic name of lactic acid. This one is quite easy. First, we need to know which one is the higher priority when it's naming. Carboxylic acid is always the highest priority. So means the ending name, it must be acid. So here, this longest carbon chain is 3 carbon. So it's the, therefore, propanoic acid. So 3 carbon carboxylic acid is propanoic acid. And now the OH here is the substituents. And these substituents is bonded to the second carbon. So we call 2-hydroxy. So it's the 2-hydroxy propanoic acid. This is the name. We name the substituents first, then followed by the ending name, means the acid. Part 3. Lactic acid forms a hydrogen bond with water. Complete figure 4.2 to show the formation of a hydrogen bond between 1 molecule of lactic acid and 1 molecule of water. Actually, no need to really draw like what I did. You just need to draw one of this, right? As long you can show the hydrogen bond. Okay, this oxygen can form hydrogen bond with H2O. Okay, make sure you show the lone pair on the oxygen, and this one, this dotted line, so it's a hydrogen bond, and this hydrogen bond need to be 180 degree, and you must show the dipoles as well. Partial negative on oxygen, partial positive on the hydrogen, and partial negative on the oxygens here. So at least must show the 3 dipoles. Okay, this is how to draw the hydrogen bond. Okay, and it's between the now oxygens and the H in the water. It can actually be another way. Let's say now, because this H is bonded to oxygen, so this hydrogen can form hydrogen bond with the water. So now the water not really use hydrogen. Now the water can use the oxygen. The lone pair on oxygen will form this hydrogen bond with this hydrogen. Okay, of course you need to make sure again it's 180 degree and must show all the dipoles. Partial positive on this hydrogen, partial negative on oxygen, partial positive on this hydrogen. Okay, of course, this one you can follow the similar way as I told you just now. Okay, you just need to draw one because it's already mentioned 1 molecules of lactic acid and 1 molecules of water. Okay, so for this B, two possible synthesis of this pyruvic acid are shown in this figure 4.3 and 4.4. Each synthesis has a total 3 steps. So first step, second step, third step. Okay, let's start the first one. Okay, we start from the propene. From propene with the bromine, we know that is the electrophilic addition. So the 2 bromine added to this double bond and form this compound. And after the second step and third step is form this pyruvic acid, means it has carbonyl and these carboxyl groups. So how to form this? Then we need to think how to get rid of this bromine at the same time can form this. So it's very easy. Just follow what I telling you now. Okay, the second step, it should be nucleophilic substitution, means we try to substitute the bromine here, okay, using the sodium hydroxide in water solvent. When the sodium hydroxide in water means substitutions will happen, not elimination. So therefore, both bromine will substitute by OH form this alcohol. Okay, and this alcohol will further oxidize to form this one. Okay, how? This hydrogen and these hydrogens will remove, form this carbonyl group. And of course, this hydrogen and these hydrogens will remove to form this aldehyde. And this aldehyde group can further oxidize to form this carboxylic acid. Okay, after this oxidation, then it can form this pyruvic acid. Okay, means the first step need to be the nucleophilic substitution, which involve sodium hydroxide in water. Second is the oxidizing agent. See, oxidizing agent. So means third step is oxidation. Second step is nucleophilic substitution. For this figure 4.4 here, it started with the ethana. After the first step, second step is form the lactic acid, and this lactic acid will undergo oxidation to form this pyruvic acid. For this third step is very easy. The H here and H here will removed, and therefore it can form this pyruvic acid. Okay, the key is this one. Okay, if you look carefully, ethana just 2 carbon. Lactic acid it has 3 carbon. See that? So when the intermediate or the product it has 3 carbon and the reactants is just 2 carbon, we know that it must involve cyanide. So means it will form nitrile later. So the first step is going to be nucleophilic addition, which involved the cyanide ion. Okay, you can use HCN and KCN, or you can use the sodium cyanide with H2SO4, because sodium cyanide with H2SO4 will form HCN. Okay, either one. Okay, so let's start the reaction. This is for the one from ethana. Okay, so the ethana for the first step, it will undergo the nucleophilic addition. The cyanide ions will attack this carbonyl carbon. So after that, it will form this intermediate, and the oxide here will try to get the protons from HCN. C H bond break. Okay, the pair of electrons, okay, will go to this carbon, and it will form the cyanide ion. So that's why cyanide ion is actually the catalyst. Means it can, because it can regenerate. Okay, but this is not the key now. So after it reacts, it will form this cyanohydrine, and this cyanohydrine will undergo second step, so which is the hydrolysis. The nitrile groups here need to undergo hydrolysis okay, CN triple bonds break, this carbon after the hydrolysis will form COOH. So this carbon will form COOH, and the nitrogen will form ammonia. A nitrogen here we don't care. So means after the hydrolysis we will get this one. Means the CN now is changed to COOH. And this one is the lactic acid. As shown in the figure, the lactic acid undergo oxidation from this pyruvic acid. Okay, why we can use the sodium cyanide with acid? Again, sodium cyanide with acid form HCN. So the HCN can use in the mechanism. Okay, so I hope you understand what I'm telling you. So let's start the part 1. Complete the diagram in the figure 4.5. Okay, this one is a mechanism. This is the electrophilic addition of the propene. First, you need to draw this, put the dipole, partial positive on this bromine, partial negative on this bromine. So just draw an arrow from this double bond and point to this bromine with partial positive. Okay, after that, okay, another one you have to show is this one. You have to show the Br-Br bond break, and these electrons will move to the bromine and it will form bromides here. And after this bromine added to this carbon, so it will form this intermediate, this carbocation. So when the carbon here get a bromine, so this carbon is electron deficient, so it's a carbocation. And this carbocation will attack by the bromide. So try to draw lone pair, charge negative and lone pair in the bromide, and draw the arrow from this lone pair point to this carbocation. Okay, then another CBr bonds will form, okay, and it will form this product. Okay, now part 2. Write an equation for the oxidation of lactic acid to the pyruvic acid. The third step in the figure 4.4. The step, okay, this one. From this lactic acid to this pyruvic acid. Okay, very easy. This one is the lactic acid. So we put the oxidizing agent. We just put the oxygen with square bracket. So the H here and H here, these two H will be removed and it will form this carbonyl group. And of course the two H will combine with the oxidizing agent, form H2O. So this is the equation. Okay, part 3. This one you just need to fill up the table. Is exactly what I told you just now. For this one, the figure 4.3, the propene. First step, use bromine. Then second step is the substitution, nucleophilic substitution, which need to use the sodium hydroxide in water. After that, it need to undergo oxidation. So we use the acidified potassium dichromate. And for the figure 4.4, the first step is the nucleophilic addition. I already told you just now. We can use the HCN and KCN, or the sodium cyanide with the H2SO4. And of course, the second step is the hydrolysis. You can put dilute HCl, or you put H plus aqueous, same thing. And after that, last step, same, is oxidation. We use acidified potassium dichromate. Okay, that's all. Thank you.